Point addition. The algebraic approach. Welcome to the channel. Please consider subscribing. I produce videos daily covering a wide variety of cloud topics with focus on networking. Also, hit the bell icon to get notified of new videos. Today we're diving deep into elliptic curve point addition using pure algebra. While the geometric picture of drawing lines through points is beautiful and intuitive, it's the algebraic formulas that we actually use in practice. Understanding where these formulas come from will demystify elliptic curve cryptography and show you that there's no magic involved, just elegant mathematics. Point addition is the fundamental operation that makes elliptic curves useful for cryptography. When we add 2 points P and Q on an elliptic curve, we get a third point R, which is also on the curve. The geometric interpretation involves drawing a line through P and Q, finding where it intersects the curve a third time, and then reflecting that point. But how do we actually calculate this? Algebra provides us with a systematic method to compute point addition, one that works whether we are using real numbers or finite fields. We'll work through the complete derivation step by step, then apply it to concrete examples. By the end, you'll be able to add any 2 points on an elliptic curve using nothing but basic algebra. This is the same method used in Bitcoin's ECDSA signatures and TLS key exchange. You'll be doing real cryptographic mathematics. The setup. What we're given. Let's start by clearly defining what we have and what we are trying to find. An elliptic curve in short Weierstrass form has the equation y squared equals x cubed plus ax plus b. This is a curve, a set of points, x, y, that satisfy this equation. The curve is symmetric about the x-axis because if x, y is on the curve, so is x, negative y. We're given 2 points on this curve. Let's call them P equals x1, y1, and Q equals x2, y2. The subscripts 1 and 2 just identify which point we're talking about. Point 1 is P, and point 2 is Q. Since these points are on the curve, they must satisfy the curve equation. That means y1 squared equals x1 cubed plus a times x1 plus b, and the same equation applies to point Q. Our goal is to find a third point R equals x3, y3 that represents the sum P plus Q. We use subscript 3 because it is the third point, the result of adding the first 2 points. This result must also satisfy the curve equation, so we need to find formulas that tell us what x3 and y3 are in terms of x1, y1, x2, and y2. The key insight is that we're going to use the line that passes through P and Q. This line has a simple equation. Y equals lambda times x plus c, where lambda is the slope and c is the y-intercept. Once we know this line, we can find where it intersects our curve, and that will give us our answer. The algebra gets a bit involved, but every step is straightforward, just substitution and simplification. Finding the line through P and Q. Any straight line in the xy plane can be written as y equals lambda times x plus c, where lambda is the slope, how steep the line is, and c is the y-intercept, where the line crosses the y-axis. Our first task is to figure out what lambda and c are for the line that goes through our 2 points P and Q. The slope lambda measures how much y changes per unit change in x. It is calculated as rise over run. Lambda equals the change in y divided by the change in x. Specifically, lambda equals y2 minus y1 divided by x2 minus x1. If you go from point P to point Q, you move x2 minus x1 units horizontally and y2 minus y1 units vertically, so the slope is that ratio. Once we have the slope, we can find the y-intercept c by using the fact that point P is on the line. Substituting P's coordinates into the line equation, we have y sub 1 equals lambda times x sub 1 plus circa solving for c. We get c equals y sub 1 minus lambda times x sub 1. So, our complete line equation is y equals lambda x plus, in parentheses, y sub 1 minus lambda times x sub 1. It is worth noting that this only works if x1 is not equal to x2. If they are equal, the line is vertical, and the slope is undefined. That is a special case we will handle later when we talk about point doubling and the point at infinity. For now, we are assuming we have two distinct points with different x-coordinates. Finding where the line meets the curve. Now we have a line y equals lambda x plus c and a curve y squared equals x cubed plus x plus b. We want to find all the points where the line intersects the curve. That is, all points, x, y, that satisfy both equations simultaneously. The way to do this is by substitution. We'll replace y in the curve equation with the expression from the line equation. Taking the line equation y equals lambda x plus c and substituting it into the curve equation, we get parentheses lambda x plus c close parentheses squared equals x cubed plus x plus b. Now we need to expand the left side. Using the formula parentheses a plus b close parentheses squared equals a squared plus 2ab plus b squared, we get lambda squared x squared plus 2 lambda cx plus c squared equals x cubed plus x plus b. This is an equation in terms of x only. The y variable has been eliminated. Let's rearrange this into standard polynomial form by moving everything to one side. X cubed minus lambda squared x squared plus open parenthesis a minus 2 lambda c close parenthesis x plus open parenthesis b minus c squared close parenthesis equals 0. This is a cubic equation, a polynomial of degree 3 in x. The fundamental theorem of algebra tells us that a cubic equation has exactly 3 roots, solutions, counting multiplicities. These 3 roots are the x-coordinates of the 3 points where the line intersects the curve. We already know 2 of them. They are x sub 1 and x sub 2, the x-coordinates of our original points P and Q. The third root, which we will call x sub 3, is the x-coordinate of the third intersection point. Our job now is to find x sub 3. Step 3. Using Vieta's formulas to find x sub 3. Vieta's formulas describe beautiful relationships between the roots of a polynomial and its coefficients. They are named after François Vieta, a 16th-century French mathematician. For a cubic polynomial where x cubed plus b times x squared plus c times x plus d equals 0, and with roots r sub 1, r sub 2, and r sub 3, Vieta's formulas tell us that the sum of the roots equals negative b. This means r sub 1 plus r sub 2 plus r sub 3 equals negative b. Our cubic equation is x cubed minus lambda squared x squared plus a minus 2 lambda c, x, plus b minus c squared, equals 0. Comparing this to the standard form, we see that b equals negative lambda squared. Therefore, by Vieta's formula, the sum of the 3 roots is x1 plus x2 plus x3 equals negative lambda squared, which simplifies to x1 plus x2 plus x3 equals lambda squared. This is useful because we can now solve for x3. Rearranging the equation, x3 equals lambda squared minus x1 minus x2. This is one of the key formulas for elliptic curve point addition. Notice that it only depends on the slope, lambda, and the x-coordinates of P and Q. We square lambda and subtract the 2 x-coordinates to get the x-coordinate of the result. You might wonder where the lambda squared comes from. Why do we square the slope? It is because when we substituted y equals lambda x into y squared, we obtained lambda x, all squared, which then became lambda squared x squared. This lambda squared became the coefficient of x squared in our cubic, and Vieta's formulas relate that coefficient directly to the sum of the roots. It all fits together beautifully. Step 4. Finding y sub 3 by reflection. We've found x sub 3, the x-coordinate of the third intersection point. Now we need y sub 3, the y-coordinate. At this point, we need to think carefully about what we're actually computing. The third intersection point where the line meets the curve has coordinates x sub 3, y sub 3 prime, where y sub 3 prime is on the line. But the elliptic curve group operation is defined to include a reflection over the x-axis. So the actual result r equals x sub 3, y sub 3, has y sub 3 equal to negative y sub 3 prime. Why do we reflect? It is a convention that makes the elliptic curve points form a group, a mathematical structure with nice properties like associativity, identity, and inverses. The reflection ensures that if we add a point to its reflection over the x-axis, we get the identity element, the point at infinity. Without the reflection, the algebra would not work out to give us a proper group. So, let's find y3 prime. Since the point x3, y3 prime, is on the line y equals lambda x plus c, we have y3 prime equals lambda times x3 plus circa. Recall that c equals y1 minus lambda x1. Substituting this, we get y3 prime equals lambda x3 plus y1 minus lambda x1. We can then rearrange this as y3 prime equals lambda times the quantity x3 minus x1, plus y1. Wait, that's not quite right. Let me recalculate. We have y3 prime equals lambda x3 plus circa. Substituting for c, that becomes lambda x3 plus the quantity y1 minus lambda x1. Expanding that, it simplifies to lambda x3 plus y1 minus lambda x1. And finally, grouping the lambda terms, we get lambda times the quantity x3 minus x1, plus y1. Actually, I need to be more careful. Let's use the fact that y3 prime equals lambda x3 plus c, where c equals y1 minus lambda x1. So, y3 prime equals lambda x3 plus y1 minus lambda x1. Now we reflect. y3 equals negative y3 prime, which equals negative open parenthesis lambda x3 plus y1 minus lambda x1 close parenthesis. This simplifies to negative lambda x3 minus y1 plus lambda x1, which can be rewritten as lambda open parenthesis x1 minus x3 close parenthesis minus y1. That's our formula for y3. The complete point addition formulas. Let's summarize what we've derived. To add 2 points, p equals x1, y1, and q equals x2, y2, on an elliptic curve, we use 3 formulas. First, we calculate the slope. Lambda equals the quantity y2 minus y1, divided by the quantity x2 minus x1. This is just the standard slope formula from coordinate geometry, rise over run. Second, we calculate the x-coordinate of the result. x3 equals lambda squared minus x1 minus x2. This comes from Vieta's formulas applied to the cubic equation we get from the line curve intersection. We square the slope and subtract both original x-coordinates. Third, we calculate the y-coordinate. y3 equals lambda times open parenthesis x1 minus x3 close parenthesis minus y1. This comes from the line equation combined with reflection over the x-axis. Notice that we use x1 in this formula, not x2. We could also write it as lambda times open parenthesis x2 minus x3 close parenthesis minus y2, which gives the same result. These 3 formulas are universal. They work for elliptic curves over real numbers, over complex numbers, over finite fields, anywhere the algebra makes sense. In cryptography, we use these exact formulas over finite fields, just replacing regular division with modular inverse. The beauty of algebra is that once we have derived these formulas, we can apply them in any setting. That is the power of abstraction in mathematics. Worked example setting up. Let's work through a complete example using real numbers. We'll use the elliptic curve y squared equals x cubed minus 2x. This is a curve with a equals negative 2 and b equals 0. It's a nice curve to work with because the arithmetic stays relatively simple, with no huge numbers or complicated fractions until the end. First, let's verify that we have 2 valid points on this curve. Take p equals 2, 2. Is this on the curve? Let's check. Left side is y squared equals 2 squared equals 4. Right side is x cubed minus 2x equals 2 cubed minus 2 times 2 equals 8 minus 4 equals 4. Yes, 4 equals 4, so p is on the curve. Now, take q equals -1, 1. Is this on the curve? For the left side, 1 squared equals 1. For the right side, -1 cubed minus 2 times -1 equals -1 plus 2, which equals 1. Yes, q is also on the curve. Great, now we are ready to compute p plus q. Our goal is to find r equals x sub 3, y sub 3 such that r equals p plus q. We will use our three formulas. First calculate lambda, then x sub 3, then y sub 3. Let us work through each step carefully, showing all the arithmetic. Worked example. Part 2, computing the result. Step 1. Calculate lambda. Lambda equals y sub 2 minus y sub 1 divided by x sub 2 minus x sub 1. Our points are p equals 2, 2, and q equals -1, 1, so x sub 1 equals 2, y sub 1 equals 2, x sub 2 equals -1, y sub 2 equals 1. Therefore, lambda equals 1 minus 2 divided by -1 minus 2 equals -1 divided by -3, which equals 1/3. The slope of the line through P and Q is 1/3, a gentle upward slope. Step 2. Calculate x sub 3. X sub 3 equals lambda squared minus x sub 1 minus x sub 2. We have lambda equals 1/3, x sub 1 equals 2, x sub 2 equals -1. So, x sub 3 equals 1/3 squared minus 2 minus -1, which equals 1/9 minus 2 plus 1, which equals 1/9 minus 1, which equals 1/9 minus 9/9, which equals -8/9. The x-coordinate of our result is -8/9. Step 3. Calculate y sub 3. Y sub 3 equals lambda times the quantity x sub 1 minus x sub 3, minus y sub 1. We have lambda equals 1/3, x sub 1 equals 2, x sub 3 equals -8/9, y sub 1 equals 2. So, y sub 3 equals 1/3 times the quantity 2 minus -8/9, minus 2. This equals 1/3 times the quantity 2 plus 8/9, minus 2. Now, 2 equals 18/9, so 2 plus 8/9 equals 26/9. Therefore, y sub 3 equals 1/3 times 26/9, minus 2. This equals 26/27 minus 2. Converting 2 to 27. 2 equals 54/27. So, y sub 3 equals 26/27 minus 54/27, which equals -28/27. Our result is r equals p plus q equals -8/9, -28/27. Let's verify this is actually on the curve. Left side. -28/27 squared equals 784/729. Right side. -8/9 cubed minus 2 times -8/9 equals -512/729 plus 16/9. Converting 16/9 to 729. 16/9 equals 1296/729. So the right side is -512/729 plus 1296/729 equals 784/729. Perfect. Both sides equal 784/729, confirming our answer is correct. Summary and key takeaways. We've derived the complete algebraic formulas for elliptic curve point addition from first principles. The process involves finding the line through 2 points, substituting into the curve equation to get a cubic, using Vieta's formulas to find the third intersection point, and reflecting over the x-axis. No geometry needed. Just algebra. The key formulas are: lambda equals the quantity y2 minus y1, all over the quantity x2 minus x1. x3 equals lambda squared minus x1 minus x2. And y3 equals lambda times the quantity x1 minus x3 minus y1. These three formulas completely determine the sum of 2 points on an elliptic curve. They work over any field where division makes sense: real numbers, rational numbers, complex numbers, or finite fields. In cryptography, we use these same formulas, but we operate over finite fields, modulo a prime number. The only difference is that division becomes multiplication by the modular inverse. The algebraic structure is identical. That is why studying elliptic curves over real numbers provides intuition that transfers directly to the cryptographic setting. Understanding this algebra is crucial for implementing elliptic curve cryptography correctly and for debugging when things go wrong. You now have the mathematical foundation that powers Bitcoin, TLS, and countless other security systems. Pretty amazing that such elegant mathematics has such powerful real-world applications. Thank you for your attendance. Please consider subscribing to the channel.